Have you ever looked at the night sky and wondered what really happens to all those stars when they die? Because the truth is, stars don't just fade away. Some collapse so violently they rip themselves apart. Some explode brighter than entire galaxies. And a few, the most extreme, die in a way that creates the closest thing our universe has to a cosmic monster. Today, we're diving into the full life and death cycle of stars, carefully, step by step, from calm red giants, to white dwarfs, to neutron stars, and finally, the most terrifying death of all, a black hole. Welcome to Daily Dose of Space. Let's begin. Why stars die at all? Stars seem eternal, but they absolutely aren't. Every star is balancing between two forces: gravity, trying to crush it inward; nuclear fusion, pushing outward. As long as it fuses hydrogen into helium, the star is stable, but hydrogen doesn't last forever. And that's when the countdown to death begins. More massive stars burn fuel faster, so even though they're larger and hotter, they actually live much shorter lives. Lifespans: red dwarfs, up to 10 trillion years. Sun-like stars, about 10 billion years. Massive stars, just millions of years. When a star runs out of hydrogen, the real drama starts. Sun-like stars, how you die quietly. When stars similar to our sun begin to run out of hydrogen in their cores, fusion slows down. Gravity starts winning, and the core contracts. But this compression heats it up, and the outer layers expand. Red giant phase. Our sun will swell to around 100 times its current size. Earth? Toast. Completely engulfed or roasted. The outer layers become cooler and redder, hence red giant. Inside, the core gets so hot it ignites helium fusion, producing carbon and oxygen. Helium flash and instability. Helium fusion is short-lived, only a few 100 million years. When helium runs out, the star has nothing left to fuse. Gravity crushes the core tighter and tighter, but the outer layers? They get pushed away. Planetary nebula. A sun-like star gently sheds its outer layers into space. This creates the beautiful glowing structures we call planetary nebulae, even though they have nothing to do with planets. The white dwarf. All that remains is a white dwarf, a dense, Earth-sized stellar core glowing with leftover heat, mass about 0.6 solar masses. Size similar to Earth density. A teaspoon weighs 10 tons. White dwarfs don't explode unless they interact with a companion star. If not, they simply cool for trillions of years and fade out. This is the calm, gentle death of an ordinary star. Massive stars, the violent path. For stars at least 8 times the mass of the sun, everything is different. Everything is more extreme. Massive star life cycle. Instead of stopping at helium, massive stars fuse. Carbon, oxygen, neon, magnesium, silicon, until finally, they create iron in their cores. And iron is a problem. Why iron kills stars. Fusion releases energy until you reach iron. Fusing iron consumes energy. So once iron appears, the star loses its last source of pressure. Gravity sees an opportunity and collapses the entire core in a fraction of a second. Supernova, a star's final scream. The core collapses at 70,000 kilometers per second. Temperatures exceed 100 billion degrees. Electrons and protons merge into neutrons. Then, the collapse rebounds. This creates the most intense explosion the universe naturally produces. A Type II supernova, a single supernova, becomes brighter than billions of suns, produces gold, uranium, and other heavy elements, sends shockwaves across light years. Every atom of gold you've ever seen, your jewelry, your electronics, was created in the last moments of dying massive stars. It's poetic and terrifying. What's left behind? If the collapsing core weighs between 1.4 and approximately 2.5 solar masses, it becomes a neutron star. This is one of the strangest objects in the universe. Neutron star facts. Diameter, 20 kilometers. Mass, 1.4 to 2.5 suns. Density, a teaspoon equals Mount Everest. Surface gravity, 200 billion g. Speed, many rotate hundreds of times per second. These stars produce pulsars, magnetars, fast radio bursts. Neutron stars are already extreme, but some stars are even heavier, and their fate is the most dramatic of all. The ultimate death, black holes. If the remaining core weighs more than approximately 2.5 solar masses, nothing can stop gravity. Not pressure, not nuclear physics, not even neutron degeneracy. The star collapses past the point of no return, the event horizon, and forms a stellar mass black hole. Inside, physics itself breaks. Space and time curve into something we can't fully describe. Black holes formed from massive stars typically weigh 5 to 20 solar masses. But in the centers of galaxies, black holes can reach billions of solar masses, billions of times more powerful, shaping the evolution of entire galaxies. The death of a star can create the most powerful gravitational engine in existence. Every star in the sky is living through one of these stages right now. Some are calm and stable. Some are nearing their final acts. And some, the most massive, are already collapsing, exploding, and creating black holes on the far side of the Milky Way. And one day, even our sun will become a red giant, shed its outer layers, and leave behind a white dwarf slowly cooling in the dark. The universe might feel eternal, but the stars we see tonight, they're all temporary, cosmic fireworks in slow motion. Thanks for watching Daily Dose of Space. If you want more deep science explainers like this one, you know what to do.